with everyone's favorite XKCD comic. So in this comic, they are trying to figure out if jelly beans cause acne. Okay, so these are a bunch of scientists, and they have a bunch of people eating jelly beans, and then they measure it and see, do these people have more or less acne than usual? And so this person runs onto the scene and says, jelly beans cause acne. Scientists, investigate. But we're playing Minecraft. Fine. We found no link between jelly beans and acne, p greater than 0.05. So they did their statistics, and they said, look, the chance that, based on the data we saw, there is no link between jelly beans and acne. The relationship has a p-value of greater than 0.05, and therefore we think there's no link. That settles it. But I hear it's only a certain color that causes it. Scientists, but Minecraft. Okay, let's see what the scientists do. So the scientists now switch into hardcore testing mode, and they're saying, they're testing all the colors individually. We found no link between purple jelly beans and acne. We found no link between brown jelly beans and acne. We found no link between pink jelly beans and acne. We found no link between blue jelly beans and acne. Blah, 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 blah. Salmon, red, turquoise, magenta, yellow, gray, tan, cyan, green. Oh, wait a second. We found a link between green jelly beans and acne. P is less than 0.05. Whoa! Okay, but then we go back. Mauve. The mauve jelly beans are not correlated with acne. We found no link between beige jelly beans and acne. We found no link between lilac jelly beans and acne. Black, peach, orange. And then, of course, what is the headline after all this experimentation? News. Green jelly beans are linked to acne. 95% confidence. That's the p-value is less than 0.05. And the question for you that I want you to answer now, based on this comic in this universe, do you think green jelly beans cause acne or not? Assuming the scientists did all their experiments correctly, are you convinced by this newspaper headline? Yes or no? Okay, I'll let you think carefully for a while. All right, 15 seconds left. Put in your guesses. Maybe you have no idea. Then you gotta pick one at random if you have no idea, I guess. Okay. So once again, of course, we cannot be sure without the actual data, right? What is going on? But we can make a guess based on what happened. All right. Let's see what people said. All right. Were people convinced or not? Where are the results? Okay, 7 to 12. 7 people said yes, they do. 12 people said no, they don't. And I think the no, they don't, quite a popular answer here. On the face of it, it's kind of hard to describe because in real life, sometimes you don't get to see all this stuff, right? In real life, sometimes you just see the newspaper headline. You just see this newspaper headline. And this newspaper headline leads to one paper, right? It leads to only the picture of this panel from the green. And then, like in that universe, if you see green jelly beans cause acne and you see this experiment, we found a link between green jelly beans and acne with p less than 0.05, then you're like, okay, I guess the stats are there, right? So somehow seeing all this extra information is making us skeptical about the green. Does anyone have a reason or a way they would say, why is it that all this other stuff is making you skeptical about the link between the green jelly beans and the acne? What is it about everything else that makes you skeptical? Yeah.
There's 20 other panels or 19 other panels?
Yes, that's right. That's a very good observation. There's 20 panels in total. 5 by 1, 2, 3, 4. So what's special about the number 20?
Well, if there's a 5 chance you're wrong, and 1 in 5 panels gives us a positive, then it is entirely possible that's the one where you're wrong.
Yeah, that's right. Okay, so this is a very good. This is getting into what does this p-value mean, which we'll write down in a second. But essentially, the p-value of 0.05, when I don't know, I think it was some random statistician, Ronald Fisher, decided on this value 5%. And in some old paper. And I think even in that paper he wrote, I just made this up. Don't use this as the standard for reality. But for whatever reason, people have stuck to that and used it for everything. When the p-value is set to 5%, that means that we consider things to be an effect if the chance of that happening due to chance is 5% or less. If you've played the role-playing game Dungeons or Dragons, you have a 5% chance of rolling the 20 on your 20-sided dice. And so when you roll the dice and it comes up 20, you go, whoa, that's something cool that just happened. But of course, something cool that just happened should happen just by chance 1 out of 20 times. And we have 20 experiments here, and in 1 of the 20 times, something cool happened. So we should not maybe think that there's something interesting going here. Maybe it just happens just by chance. So let's actually write this down, because this is an important concept. And here's my whiteboard. So the p-value, what is a p-value? Okay, and it's supposed to measure how, let's put this in quotes, surprising something is. So the p-value measures how surprising something is, and we usually say very surprising. That means we think there is an effect. So in other words, when we see something really surprising, we're like, oh, maybe there's something going on there. When we see a surprising number of people who have acne who ate green jelly beans, then we say, oh, that's very surprising. Maybe there's an effect between the green jelly beans and the acne. And so we set the threshold to 0.05, which is also known as 5%. And so what does very surprising mean? Very surprising means happening less than 5% of the time. So very surprising means less than 5% of time. Okay, and so in our jelly bean comic, because we did 20 different things, even though seeing something surprising happen is surprising, if you do it 20 times and our threshold is 5%, you should expect one surprising thing to happen in 20 times. Just like a dice, there's no effect in a dice, but if you roll it 20 times, one of the times is likely to be a 20. That doesn't mean that the dice is rigged or something. It's just by chance. That is the very vague, what I've written here on the board is a very vague, like the idea of this p-value. But there is a very important thing to make this more specific. So right now, this is kind of the idea we want, but doesn't have the math specifics to it. And there's one important thing that should be on the board that I'm missing. Does anyone know like a better answer to what is a p-value? And again, p-values are one of those things, even lots of people who've taken statistics class mess them up. Lots of doctors mess them up. This newspaper headline for sure messed it up. So when people say 95% confidence, I find that very misleading. When someone wrote only 5% chance of coincidence, also quite misleading. So what are we talking about here? Like these when I wrote very surprising and 5% chance, a 5% chance of what? Does anyone know the little thing that needs to go up here to make it correct that we're talking about? I heard someone say something. Is that right? There's a magic word. Let me do a hint. P-value. They measure how surprising something is, and this is the part that is missing. let's add it in. Surprising is, how surprising something is, by the blank hypothesis. So lots of people now know that the word is null. So you have at least this in your brain, that hypothesis and null go together. What is the null hypothesis? What a null hypothesis means, null hypothesis means, what does it mean? You know, you have it in your brain, null hypothesis. What is the null hypothesis?
There's no relationship between the jelly beans.
Yes, very nice. In this case, the null hypothesis is, let me write that down as an example. That is that you said it perfectly right. So example, no relationship between jelly beans and acne. And in general, the null hypothesis means what we think is going on, and null means nothing, right? So the null hypothesis means nothing is going on, means boring randomness only. Boring randomness. Or in other words, no relationship. No relationship. And in different situations, that will mean different things. Okay. We're going to see some examples now. But in our case, it means there is no relationship between jelly beans and acne. Whether or not you eat a lot of jelly beans, it does not affect how much acne you have. And the nice thing about the null hypothesis is under the null hypothesis, we really can measure how these things are. So when I say something is very surprising, I calculate the probability according to the null hypothesis. And so very surprising means very surprising under the null hypothesis. So assuming, let me write assuming, that's a better word than under. Assuming the null hypothesis. So if we were to assume that the green jelly beans have no relationship to the acne, then it would be very surprising to see the effect that we did. So a very surprising assuming the null hypothesis means there is an effect, or in other words, AKA, the null hypothesis is unlikely to be true, AKA the null hypothesis is unlikely to be true. Right? That's the idea. And again, you gotta be careful, like unlikely is, maybe I shouldn't say unlikely, but okay, I'm just gonna leave it. We're not measuring the probability that the null hypothesis is true or false. We're measuring the probability according to the null hypothesis, and then if it's small enough, then we're like, hey, something's fishy here. This null hypothesis is probably not right. If the null hypothesis was true, the thing we're seeing is very surprising. That would be bad. And we normally set this threshold to 5% of the time. So very surprising means less than 5% of the time by the null hypothesis, assuming the null hypothesis. Okay. So in other words, going back to the comic, the way the scientists are, or what they're actually doing is they are assuming that there is absolutely no relationship between jelly beans and acne, and then they're looking at groups of people who have eaten various jelly beans, and they're saying, let's assume there's no relationship between jelly beans and acne. Let's calculate how likely it is we're seeing the amount of acne that we're seeing. And in this one, they saw a lot of acne. But the problem is, because there were 20 samples, in one of the 20 samples, there's likely to be a lot of acne just by chance. So looking at this one subgroup and sort of ignoring the fact that you've done 19 other experiments just like it is sort of bad statistics. If you split up a random sample into 20 groups, one of the groups is going to have more than the other ones just by chance. And if you haven't accounted for that in your testing, then you are doing bad statistics and things will not work. Of course, sometimes you do want to split it up by color, and you just have to be careful. This kind of situation is called the multiple hypothesis testing problem. So the jelly bean comic is related to the multiple hypothesis testing problem. And the problem is basically based on this system of measuring when we think things are going to happen, very surprising if we have a lot of different things that are, what is very surprising one time and what is very surprising in a group of 20 are different things. So the multiple hypothesis testing problem is how do we measure very surprising? How do we measure very surprising when there are multiple groups? Okay, and this is the important thing, is what is very surprising when you just have one group, and what is very surprising when you have 20 different groups should be different, right? If you roll a dice one time and it came up 20, you'd be like, whoa, maybe that dice is always coming up 20. Maybe that's a very good dice. But if you roll a dice 20 times and one time it came up 20, then you'd be like, hey, that's a pretty boring dice. And so the multiple hypothesis testing problem is exactly saying, how do we account for the fact that we're doing multiple tests? And the key thing is, we need a way to measure variability. We must have a way. So it's not enough to just know what is a big effect or not. We need to know how much variability there is. We need to be able to measure variability. Able to measure variability. And that's the topic we're going to discuss today. How do you measure the variability in measurements? So in other words, how can you account for things? If you know how much things are likely to shift around, you can sort of get to answers like this question. And there are a few different ways to measure variability. I'm going to list some of them. Here are some solutions. One is theory. Let's say theory. Pure statistics theory. I'll show you an example of that. We've seen some examples of this, actually. Number two is something I call Monte Carlo methods, and specifically Monte Carlo. In our case, I'm going to do Null Hypothesis Monte Carlo, and I have a nice example of the Null Hypothesis Monte Carlo, where you can skip doing theory, and in a lot of situations, this is a great tool. I think a lot of statistics, the theory has been overemphasized because it was before computers were big enough to do good Monte Carlo. But nowadays, computers are very good. And so there's a lot you can do with Monte Carlo that can sort of replace theory. And the actual topic that I want to get to is the bootstrap. The bootstrap. And the bootstrap is, again, is kind of like a Monte Carlo. But it's a sort of a specific way of doing Monte Carlo to check how much things are varying in your data set. OK, so that's what we're going to do. Let's start with this jelly bean problem. Let's start with this jelly bean problem, which I have over here. Jelly beans, OK. And so I made a little simulation of the jelly beans. And here I have 20 types of jelly beans. I didn't give them color names. I just gave them numbers because I'm lazy. There's jelly bean type 0 all the way up to jelly bean type 19. And each of the jelly beans has an effect size. So you see jelly bean type 0, negative. The people who ate jelly bean type 0, they had less acne than normal. People who ate jelly bean type 9, they had a little bit more acne than normal. And the really exciting thing is here, jelly bean type 11, those people had the highest amount of acne. They had 0.2. And the question we have to ask ourselves, is 0.2 a lot or not? Right? Like, is this 0.2 a lot higher than we would expect in a group of 20 jelly beans? Or is 0.2 about what we'd expect if there was no effect? That's the kind of question we have to answer. And to understand that, we need to understand the variability. Is it kind of varying from negative 0.2 to positive 0.2? Or is it like negative 0.1 to 0.1, in which case this would be a really big number? So that's really what we're asking. Is 0.2 a big number or a small number in the context of our sample? And the model that I have here is that every jelly bean, essentially this is my null hypothesis, is I am assuming that every individual person who eats a jelly bean, they have some amount of acne that is on a scale of -1 to 1. -1 to 1, and it's uniformly at random. So the amount of acne you have is not affected by which jelly bean you are, and it's a random number between -1 and 1, uniformly at random. And then to measure a group, I take the median. Now the median is a nice number. It has some nice properties, and it is, in particular, it is robust. So if some weirdo person has something else going on with them, hopefully the median will not be highly affected, which is why I'm using the median. I'm also using the median because if you do the mean, then it's a little bit easier to do. So the median makes it harder. But in general, like you have an assumption on your data, and then you do something crazy to it, and that is like the thing you're measuring. In your projects, for example, you're doing some weird combination of doing subset selection or whatever, and measuring some combination of your data. This in general can be very complicated, and the point is we want to look at methods that can handle no matter what you're doing to it. So we want to understand the median. The null hypothesis is that all the data is -1 to 1, and the value we're measuring is the median. And so like the mathematical question that we're answering is how much variability is there in the median? Let me write this down. Okay. Okay. All right. So example. Take the null hypothesis for our particular purpose. Hypothesis is that x1, x2, ... xn are IID. They're independent and they're uniform between 0 and 1. And we see the median of x1 to xn. That's what we're looking at. So in other words, we want to understand the variability of this quantity. This quantity is what we would call a statistic. Which is where the field of statistics gets its name from. A statistic is a number that is sort of summarizing the data, and we want to understand how much variability is there in the statistic so that we can tell in a sample of 20 of them, should the maximum be like 0.2 or should the maximum be like 0.1? Like what would be a surprising result for our thing, right? So understand goal, understand the variability, so we can tell what is surprising. So we can understand how surprising something is. Okay, that's our goal. Okay, and here's one way you could do it is with theory. So the first way I'm going to do is theory, and that's because in this particular problem it's not so hard. And I'm going to show you the theory. Here is my theory plot. Beautiful theory plot. This is the answer. It turns out the median of a lot of uniform random variables is something called a beta random variable. So this is option 1. And it has this beautiful plot. It's actually it's one of my favorite random variables. I have a nice video on this. Maybe I'll post the video as a little link. But this is just to show you, this is like what a lot of statistics PhDs do. If you were going to do your PhD in statistics, you would work out the theory and you would say, hey, based on this stuff, the median has to follow this curve. And with this curve, we can measure exactly what is the likelihood. We can say, what is the probability that it's 0.2 or more? We can figure that out exactly. In fact, did I do that in the notebook? Maybe not. Whatever. It's some plot. It has some formula. It involves this sc.beta involves the beta random variable. Let me write this down. So option 1 theory, and option 1 theory would be to prove that the median satisfies. What does it satisfy? The median of n data points, x1, ... xn, it is a beta random variable. And the parameters here are n over 2 and n over 2. And that means that the distribution is x to the power n over 2 times 1 minus x to the power n over 2 times this function called the beta function. I think it's beta, like this, n over 2, n over 2. This is the probability density function. So I call this rho of x is equal to this on 0, 1. Okay, why am I showing you this? Do you need to know this formula? No. What I'm trying to show you is that if you know how to do theory, you can calculate exactly what something is. So if the null hypothesis is simple enough, and you have really good theory, and you have good assumptions, then you can do a lot of hardcore math and figure out formulas like this. And then you can use the formulas to say how big is 0.2 or more. So 0.2 or more in our sample, we can figure out by the area under this curve. So we start at 0.2, we calculate the area. We can use some numerical integral to figure that out. That is what is nice about theory. That's option 1. there any questions or comments about option 1? Of course, option 1 would be like if we were taking a statistics class. We're not going to do option 1 in this course. We're going to do the more data-focused ways to do it. So the theory is nice, but the downsides, I'm going to give you some cons of the theory. Cons. It could be complicated. Could be complicated / hard. And it gets more and more hopeless to do theory the more complicated you get. So harder data sets / problems, it might not work. Might not work. So in other words, it's fine for the median. For the median, I got a nice answer. But as soon as you're doing like, oh, I threw some machine learning model at it, I did some neural network, then it's too hard to say in theory what would happen. So we need a more kind of like streamlined way to do it. And that is more data focused and more computer focused. So the theory is nice, but is too hard in general. When it works, it's amazing. But when it doesn't work, you need something else. And that's why the first option I'm going to show you, option 2. Option 2, this one is great, and you should learn how to do it in general. And this is called Monte Carlo. Monte Carlo. And this is Monte Carlo under the null hypothesis. So if you can define the null hypothesis well enough that you can simulate from it, you just simulate many instances of the null hypothesis. See what happens. Okay, so in other words, in our particular problem, look, I don't do any theory, just simulate doing this a million times and draw the distribution. And that is what I've done in the notebook as well. So we have in each group of jelly beans, how many jelly beans did I do? I did 101 jelly beans in each group. And so here I have sampled, I've done medians, plot, theoretical. Yeah, okay, here we go. So I've done, how many samples did I do? I did 100,000 trials where I took 100,000 copies of 101 jelly beans and I did the median. And then I plotted what was going on. And you get this nice histogram, looks like this. The histogram is basically a blocky version of the theory. The difference is, for the theory, you have to do some hardcore stats and like know the answer and figure out where this formula comes from, which could be very complicated. But for the simulation, all you got to be able to do is simulate it. And simulating it is quite easy. Look, here's the code. X equals 2 times the random number minus 1. Our random number is generating between 0 and 1. If you multiply it by 2, that's between 0 and 2. And then if you subtract 1, that's between -1 and 1. And then I did the median, np.median. In general, you could do any complicated code here, no matter how complicated it is, as long as you can write it down. The code could say, run a neural network, and then output the value of the neural network. It could be no matter how complicated it is, as long as it runs on a computer, you can do it here. And then you just plot what happens. And when you plot what happens, you can then measure how surprising or not something is. So we can see that 95% of the time, it's between -0.1 and 0.193. That means that out of a sample of 20, we would expect the maximum value to be 0.193. So is a value of 0.2 surprising? No, that's exactly what should happen if there's no effect, right? So this already answers the question from over here. Is 0.2 surprising? No, it's not. 0.2 should happen. In a sample of 20, 0.2 is about the right size for the maximum number. 5% of the time, it's larger than 0.2. So this is a very nice way to do it, is the Monte Carlo method. And I think everybody should know this kind of way of thinking about it, because it's really practical in practice. Again, the reason statistics, they don't talk about this a lot is because for a long time, computers were not able to do this. Having a computer that can do 100,000 samples of some statistical process is a relatively new invention. I'll tell you a really nice example. I'm going to do a little side quest here. So we're going to leave our jelly beans for a second to do yet another example. Another example. And that example is streaks in chess wins. Okay, and this is all, I found this really nice paper that I really enjoyed by the infamous Jeff Rosenthal. So Jeff Rosenthal is a famous probabilist at the University of Toronto. One of his claims to fame is he owns the URL probability.ca, which is a great URL. The other thing is he is Professor Slater's PhD advisor, so or one of Professor Slater's PhD advisors. So famous guy at the University of Toronto, and he has this nice paper on an investigation of probability streaks in online chess, and that leads you to this paper over here. Let's read the abstract. Chess is a strategy game. Yes, we know. Here is an interesting thing. There's this guy, Hikaru Nakamura, who is one of the top players in the world. Maybe like certainly top 5, undisputed top 5, maybe top 2, maybe top 1, depending on what you're doing. And recently, he played games of chess, and he won 46 games in a row. He won 46 games in a row. And you might say, whoa, 46 games in a row. If you're 50-50 to win a game, then getting 10 games in a row is a 1 out of 1,000 chance. Getting 20 games in a row is 1 out of 1,000,000 chance. And getting 46 games in a row is 1 with 20 zeros after it, right? So that'd be quite unlikely if you were playing chess. So one hypothesis is maybe he's cheating. Maybe he's using a computer program to play extra good chess, and maybe he's cheating. And this 46 games in a row is evidence that he is cheating. And in particular, this was a theory proposed by someone, Vladimir Kramnik, who was the chess champion for a while. So not only do people see this and go, hey, maybe that's suspicious, but this guy, Vladimir Kramnik, who is some serious guy, says that this is suspicious. And so this is like the question we're going to answer. Is streaks and chess wins? So is winning 46 games in a row evidence of cheating? Okay, right? And so the null hypothesis is he's not cheating. Null hypothesis. Not cheating. And then if we can reject the null hypothesis, that's evidence that he is cheating. Okay, I've told you how we're going to do this. This is the Monte Carlo method. I want you to take a minute and think for yourself. What exactly would you do? So you have what we have a list of data. We have a list of games, and who won and who lost. And based on your list of games and who won and who lost, how would you determine the answer to this question? Is 46 games in a row evidence of cheating or not? So I'll let you think for a second. This is what we have. I will tell you one other detail. Not only do we have a list of games, but in chess we have a list of games. We have the rating of each player and the rating of each player. In chess, there's a system of ratings called the ELO ratings, and they kind of accurately tell you how likely it is you would win against somebody else. If two players are the same skill level and they have the same ELO rating, then it really is like 50-50. But if one player is quite a bit better than the other player, then we would have, maybe it's 60-40 if one player is a little bit better than the other. So the rating of each player tells you with good accuracy how likely each player is to win. Okay. So now is the question. How do you use this data set to answer this question? Take the list of games and who won and who lost and the rating and figure out, is winning games 46 games in a row, is that evidence of cheating or not? Okay, I'll let you think for a minute because I think this is a worthwhile exercise. What would you do? What would you do? And of course, in a minute, we're gonna read exactly what Jeff Rosenthal did. But let's take a minute and just think. How do you use the list of games to answer the question? Okay. Does anyone have a good answer of what they would do to the data set? Or like a simple way to sort of do this stuff? What would you do? And the thing we're going to do is this Monte Carlo simulation. But what exactly does that mean in the chess games thing? I think for the jelly beans it's very straightforward. But for the chess games it's a little bit less straightforward. It's a good example of a real life problem. Anyone want to take a stab at it?
How big a roles are like the rating of each other, like player that I'm playing? Like,
Yes, this is a great question. Like, does the ratings matter?
yeah.
And I think the answer is the ratings matter a lot. Because if the game is 50-50, getting 46 games in a row is pretty rare. If the game is 90-10, then getting 46 games in a row is a lot less unlikely.
But isn't it like actual like, losses when like the data matters more than reading?
I think it's a combination, right? So this is absolutely true. So, and I think this is partially why it seems like such a unlikely thing. Like when you just say, hey, this guy, if the only thing you know, right? If the only thing we're told is some guy won 46 games in a row, then you're like, hey, that's crazy, right? And so it's really easy to get excited about that. In the same way, it's really easy to get excited about the jelly beans. But there are lots of other questions you can ask that will follow up. One of them is, what are the ratings? Another thing is, how many games did this guy play? 46 games in a row out of how many games? Anyone want to take a guess how many chess games this guy has played? I'll give you a hint. It's like 10,000 or something stupid like this. How many games did he play? That's fine. Yeah, he has played 57,000 games on chess.com. When you say he won 46 games in a row, seems pretty crazy. But if you say he won 46 games in a row out of 57,000 games, that seems a little less impressive. So this is like really what you got to answer. Is winning 46 games in a row out of 57,000, is that a lot? Or is that about what you'd expect, right? So you have to figure it out. Not only that, look, his win rate, he's won 45,000 out of 57,000. So he's won 80% of the games he's played. So already this is starting to seem less impressive. And this is essentially what we're going to do. We're just going to take the games, and of 57,000 games, let's re-simulate them. So this is the Monte Carlo method. We're just going to create an alternate universe. Create an alternate universe of games. And we're going to do this many times. Let's say 1,000 times. And just answer the question, in our alternate universes, how many alternate universes have greater than 46 length streaks? This is the Monte Carlo way. Maybe create is a bad word now. Say simulate. So we take the list of games. So maybe here's the list of games. There's game number 1. And then this is the, who was he playing? Who? What is their reading? And then the result. And we'll say the result in reality. Who is there? So maybe game number 1, their rating was, maybe you say their rating was 2,000. That's a valid rating in chess. And the result was Hikaru wins. The guy we're investigating, he wins. Okay? And then what we do, we have this list that goes all the way up to game 50,000. We have our big table base of all the games. Maybe this guy was a 2,500, and maybe in this one Hikaru loses. Okay? And what we do is, these were the real results. Let's pretend that we were in an alternate universe where we just resample it. So we make a simulated result. A simulated result. And maybe in our simulation, this time he loses. Maybe in our simulation, this one he loses again. So in other words, even though we only have one sample in reality of what actually happened, we can create new samples in reality as long as we know what is the probability he wins or loses. And we do this according to the probability win or equals, and it's some function of the rating. So as long as we can figure this out, some other function of the rating, and so on. I guess there's probability tie. There's only 3 things that can happen. Okay, great. So as long as we can simulate what happens, we can just run the simulation many, many times and see, is a length 46 streak, is that a lot or is that not a lot? And that's exactly what is being done in this paper. So in this paper, the first thing they do is they carefully find the probability of winning and losing. So this is the rating difference. So if you're equally rated, then it's 50-50. You're point flip to win the game or not. If you are much better, 400 points better, you are like 90% to win the game. If you are 400 points worse, you're like 10% to win the game. And this is a nice smooth curve in between. So the first thing that is being done in this paper is let's check the data and make sure that the data is consistent with the probabilities of winning and losing based on the rating difference, which it matches very well. The second thing that is being done is for ties. So what is the probability of tying a game based on the rating difference? If you're very evenly matched with somebody, then you are quite likely to tie. But if you are much better or much worse, then a tie is very unlikely. So figure this stuff out. And then we just simulate 1,000 times, like I said. This is making sure autocorrelation. Autocorrelation is making sure games are independent. Did I say that anywhere? This is checking. Did I write that anywhere in the Monte Carlo? Not cheating. So I wrote the null hypothesis is not cheating. So if they're not cheating, games are independent. And games are independent and win or lose according to rating difference. Yeah, so that's what we're assuming. We're assuming that games are independent and that you win, lose, or tie according to some formulas that we can compute that only depend on the rating difference and nothing else. And that's the first part of the paper, is making sure all those things really check. So the autocorrelation being close to 0, that means that what you did 10 games ago does not really affect your performance now. So this is very good. Okay. So now we can do simulations. These are some of the winning streaks. But the exciting thing is the simulations. Okay, let me go to the simulations. Are these the simulations? Monte Carlo. There's a nice graph. I'm looking for a nice graph. Let's see. Probability of a draw. Hey, where's my nice graph? Where's the graph? I think the graph might be. Is the graph in a different? Yeah, here it is. Nope, that's not it. Okay, hold on. I might be in the wrong one. Let's find this one. There's a nice one that has the graph. Where is it? Earlier report. I want earlier report, I think, maybe. Here it is. Okay, beautiful. Here we go. So what is this? What is this plot? This is the number of occurrences in 100 simulations. So we ran 100 simulations. I said 1,000 before, but there's only 100. And on the x-axis, we have the number of quote notable streaks. Notable streaks are, the guy who was accusing him was saying, this is crazy that it's more than this much. And how many times did that occur? In real life, there were 10 notable streaks. In the simulations, there were between 4 and 15. Having 10 is right in the middle. Like, having 10 is exactly what you'd expect. So in other words, this histogram generated from 100 samples is telling us that actually getting what we saw in real life is not that atypical, right? What we saw in real life kind of matches the typical kind of thing you would see in one of these simulations. There's another plot over here that is kind of like this, which is how unlikely was one of the streaks, and these little blue things are a histogram of all the simulations. We did 100 Monte Carlo simulations, and sometimes we get some really wild things happening. In 57,000 games, something quite unlikely is going to happen somewhere in the streak. In reality, we saw this one. That's really not atypical. So all of this is to say, what we observe, what the actual result is. Check. So this is what we do. Check. Compare simulations. Compare Monte Carlo simulations. And remember, the Monte Carlo simulations, which these assume the null hypothesis, right? They were generated using the null hypothesis. Okay, I might have spelled null hypothesis wrong. Hypothesis. There we go. To real life. So this is the whole thing. If you can make Monte Carlo simulations that assume the null hypothesis, then you can compare the real outcome to the Monte Carlo and see, is there some kind of difference? And in this situation, there is not. It's very clearly the real life thing that's labeled in red is not weirdly different than the null hypothesis. If the real life thing was like all the way over here, then you'd say, hey, only 2 out of 100 times did he do better than that. So the p-value of 5, 0.05, 5%, would say we need to be at least this much before we say, hey, that's weird. And it's really not. So in this situation, what happened in real life, winning 47 games in a row, is really not that weird, given how long he played and how much better he was than the opponent. So that's the conclusion. Here's his second most unlikely streak. So not his most unlikely, but his second most. And again, this one is a little bit higher, but nowhere near top 5, which is what we would want for a p-value of 5%. So there you go. So what's the conclusion? The conclusion is that probably there's not any evidence for cheating here. Yeah, unfortunately, the problem with these things is that when you show somebody the evidence like this, if somebody who's very committed will find a different way to phrase the question. So as soon as this was posted, the guy who was accusing him said, no, you did it all wrong. I didn't mean cheating in all the games. I meant only cheating in the 3-minute games. So then we had to redo it. So then it becomes the jelly bean problem, right? The person keeps picking different things. Ultimately, the person who is accusing him has gone on to accuse almost everybody else. So it turns out the real story here is that this guy, Kramnik, is just accusing everybody. A lot of people think that he's just quite upset that he used to be very good at chess, like he was the world chess champion in the 80s, but now there's a lot of people who are better than him, so he's just grumpy about that, and is accusing a lot of people left and right. So that's the real story. So fun fact that probability helped a little bit in identifying this. Okay, I think that's the end of my little side bracket. We're going to go back to the jelly beans. But any questions or comments about the chess example or how it works? I think this is great. This is to me, this is the kind of thing like real life data science. You have a real data set, and you want to answer a real question, right? You have a list of chess games, and by using smart thinking, you can answer a question like, is this evidence of cheating, in a pretty straightforward way. Questions? Okay, so let's move on. So we've done options 1 and 2, the theory or the Monte Carlo. We've done it for jelly beans and also for chess. And now we're going to move on to option 3, which is like the new topic, which is the bootstrap. Option 3, which is the bootstrap. And the bootstrap really, to me, is a certain way of doing the Monte Carlo. Option 3 is the bootstrap. And bootstrap really should be short for bootstrap samples. And this is Monte Carlo. This is a type of Monte Carlo where you don't even have to assume the distribution. So this is how I would summarize it in my brain. It is a type of Monte Carlo sampling. Monte Carlo sampling where you don't even know, don't assume a particular distribution. Okay, so in other words, in what I did over here with the jelly beans, with the jelly bean problem, in my little situation, I was generating this sample, right? How did I generate this sample? For the Monte Carlo, I first created new jelly beans according to the uniform distribution, and then I did the median. But what if I didn't know that the distribution was a uniform between -1 and 1? You can imagine a situation where you're collecting data, and the data is coming at you, and you don't know what distribution the data is. So you can only run this thing if you know that the x's are uniform between -1 and 1. You might not know that in real life. So what can you do instead? I'm going to show you the first thing before you do a bootstrap. I'm going to show you something that doesn't work, which is a train and a test set. Train versus test set. And in this situation, it doesn't work. Train versus test set. So for other problems, it does work, but for this one, it does not work, and you will see why. It does not work. And the reason is because blank. Because blank. We're going to fill in the blank as we go. And then we're going to see, once you figure out how to fix this train versus test set, then we're going to get the idea of the bootstrap. So here's what I'm going to try to do. I'm going to try to make these samples. I'm going to choose a subset. So here's my idea. Instead of 101 data points. Choose, let's say, training set size, training set of them, and compute the median only over the training set, the median of the training set only. Okay? And by choosing different training sets, I can choose one training set, then I can choose another training set, then I can get a lot of different values for this median. Okay, so this is my idea. This is like, I'll call this y, k is this. Training set k, I'll make k different training sets. Choose not a training set, but let's say 100 training sets at random. And we're going to compute the median of each one. And then the idea is that this is kind of like a Monte Carlo simulation where the randomness is in the choosing. By choosing a random subset of my 101 data points, we will have a training set, and we'll take the median, we'll get some value, and that is like replacing the Monte Carlo. Let's do it with, let's make the training set as large as we can. Let's make the training set, let's make it training set size out of 100. And remember the original data set is 101 data points. So in other words, out of 101 actual samples of people who ate jelly beans and had acne, we pick a random subset of 100. All right? There's 101 different ways to do it. So we can make 100 actually we can make 101 training sets. Let me add one. 101 training sets. Each of which consists of 100 people, and we leave one person out. This is like a leave one out situation, and we take the median. And then we can plot a histogram of these medians, just like we had in the Monte Carlo, and then we can compare, right? So we do a histogram, and then hopefully we get something like this, where this is matching some kind of approximation for the true value, the true theoretical value. Okay, everything I've described is a nice idea, but there is a problem. And I'm going to let you think about the problem in this mathematized question, which is here. Leave one out. Leave one out. Okay. We're trying to figure out how much variability there is. Typically, when taking the median of 101 data points, we use a train test split, where the training set is 100 data points and the test point is 1 point. What will the variability in our things? So we have, in other words, we have 101 different training sets. We can see how much it's changing. And there are 3 options. It will give a good estimate. We got to correct it, or basically nothing at all. Is the setup clear with what we're doing? It's exactly what I described on the board. Questions or comments about the setup? Okay, let me give you 2 minutes to think about it. I will give you a hint, which is think carefully about how medians work. What happens with medians? What's going on with medians? Okay. Okay. You could make the test set larger. We're not really using the test set here, right? We're just using the training set and seeing how much variability there is. So the test set being larger would help if there was some kind of measurement we did at the end, like measuring the error, right? If we had a prediction and we measured the error, then we'd want a larger test set to have less error. But here we just care about how variable it is. So we're making the test set as small as we can without making it 0. Yeah. Yeah, let me All right, 10 seconds left. Let's see what you guys think in this situation. Okay. What did people say? Ooh, okay. Nice split. Out of 21 people, 6 people think it's going to give us some good variability. 6 people think we got to correct it, and 9 people think basically nothing at all. Let's see what the graph looks like. So in the code, it just does it for you. And not only that, you could, if you thought about it hard enough and know what a median is, here is the kind of plot you would get. So in this situation, we have, I sampled 101 values. The real median was 0.4. I will tell you, this is, I did something a little silly here. In the other parts of the code, I was doing between -1 and 1. Now I'm doing it between 0 and 1. So I took 101 points between 0 and 1, and the true median of these 101 points was 0.41. And here's the leave one out analysis. So I left out 1 point at a time, and I took 101 samples of this thing. And this says what we got, 50 times the median was 0.41, and 50 times the median was 0.416. So basically, the median is always between 0.411 and 0.416. In other words, this is showing you that when you take your training set, which is 100 points out of 101, there's basically no difference at all. The median hardly ever moves. And this is a property of the median, is that the median is robust. The median of the training set is very closely, it's almost equal to the median of the whole data set. And this is a property of the median that is actually quite good. Like the fact that the median is robust, and if you change a couple points, it doesn't change much. Normally, that is a good thing. But in this situation, what's happening, we're trying to understand how much the median changes, and the median doesn't change at all when you do this. So what's going on is that it doesn't tell us anything. The correct answer is only 9 people got it right. It basically tells you nothing. If we were doing something that wasn't robust, like the mean, then you can figure out a factor that depends on the sample size. And so this is another problem, is that in this situation, I was doing something that had, the training set was 100 points, and the whole data set is 101 points. In some situations, like for example, doing the mean, then you can correct by depending on the sample size. And this is like ultimately the problem, is train versus test set in general will not work because of sample size issues, and robustness. So if something is not changing when you change certain points, then you will not be able to understand how much it's changing. So this thing is kind of doomed to fail because the training set is too similar to the entire data set, and because the training set is a different size than the whole data set. And this is the idea that the Bootstrap aims to fix, is you would like to do a training set, but the problem with the training set is it's not working because you have a different number of points and it's not changing enough. And the Bootstrap solves this. The Bootstrap is a different way of doing the training set. So this does not work. Instead, we're going to do the Bootstrap. Does not work. Does not work here. So once again, the training set and test set, we've used it before. It's very useful if you want to measure how big something is approximately, right? Like if you were using this to say, the true median is 0.412. How can we approximate 0.412? Well, that's a pretty good estimate for what the value is. It's not good at measuring the variability. So let me write that down specifically. We've used it before, but it does not work for measuring variability. Measuring variability, how much something changes. Okay, so instead, we're going to try to correct this idea. We're going to, instead of doing a training set size of 100, we're going to try to make one that size 101, and we're going to try to increase the diversity in our points. So by changing the individual points more, we're going to get something that's more dissimilar to the whole data set. It's not just a subset of the whole data set. And that will also help us figure out the variability. And that is the idea of the Bootstrap. The Bootstrap. So the idea is we're going to try to create a sample of size 101, so equal to the original sample size, equal to original sample size. So the sample size has to be the same, and it has more variation than a training set. More variation than a training set. So how are we going to achieve these two things? It's an extremely simple idea. I'm going to draw a little picture of the cartoon of the training set versus the training set that we've been doing before versus the bootstrap, which we're going to do now. You can think of the training set as a deck of cards. Deck of cards. Deck of cards. So you have your deck of cards, you have your sample number 1, you have sample number 2, all the way up to sample 101. And what is a training set? You take your deck of cards, you shuffle them, and you deal some out, right? You deal out a random sample, deal out random cards. Okay? So that is a training set. That's what we've been doing in the course. You have 101 things. You pick a random subset of size 100. You pick a random subset of size 80. These are all different things we've been doing. You can imagine it as a deck of cards. What is the bootstrap? It's not a deck of cards. It is a really big dice. Really big dice. That's the only difference. So instead of putting them as all your samples as cards, imagine they are all sides of a dice. So there's x1, that's one side of the dice. x2 is the other side of the dice. x3 is the other side of the dice. And you dot, 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 all the way up to x101. And then instead of picking a random subset by dealing out random cards, we're going to roll the dice 101 times. Roll the dice. Roll the dice. 101 times. And what is the difference? Sometimes you will see this be called without replacement. Without replacement. In other words, if a certain thing is chosen, if x4 is chosen, then it cannot be chosen more than once. But the bootstrap is, quote, with replacement. With replacement. And this means that we can pick, some data points can appear multiple times. Data points can appear multiple times. Okay. And this is the key thing. So by doing it as a dice, first of all, we can exactly choose the sample size. We can make sure the sample size is the original thing. We're not limited by the sample size. And second of all, we get more diversity because certain points can appear multiple times. We could pick x2 twice. We could pick x2 3 times. So because things appear more than once, that increases the sort of variability of the data set. And actually, it means there's a lot of nice theory that shows that this thing is exactly right to sort of capture the variability in things. So let me show you this idea of using a dice instead of using a cards. Let me show you the results in action on the median. So here is the bootstrap. What am I trying to do? Yeah, this is more train test split stuff. Okay. Okay, bootstrap. So once again, we have one data set of x's. The median, the true median was 0.52. And this is what the bootstrap does, is it shuffles, we take integers from 0 to n. These are which side of the dice you would like to take. So size equals n means I rolled the dice n times. N here was 101. This ix thing, ix stands for index, means give me 101 rolls of a dice, right? That's what it means. And when you roll dice, np.random.randint, rolling dice, you can get the same dice roll multiple times. And then I just do all the x of ix, that is exactly rolling the dice that I showed in the picture, right? So it's saying, please give me the values of the x values from this little picture, roll the dice 101 times, tell me the results, okay? And when you do that, and you take the median, then you have a lot of diversity in these samples because some numbers can appear more than once or not. And so here is what the distribution looks like. So our data, the true median of our data set was 0.52, 0.52. And in the bootstrap, in these samples, these are the results we got for the median. So 95% of the time, it's between 0.37 and 0.6. And the width of this interval is 0.24. And what that is saying is if you have, you repeated the experiment 20 times, then you'd expect about this much variation. It would vary by about 0.2, which is more in line with what is really happening than doing the train test split, which was just crazy. The train test split was giving you something really narrow because the median is too robust. So the Bootstrap sample sort of accurately captures the variation in the data. And that's it. That's the whole idea. It's a very simple idea. Is just when you want to understand the variability, create a dice with all your data, roll the dice that many times, and then you can sample from it. That's the Bootstrap idea. So it's a very simple idea, and it's a really useful thing to do. So pros, let me say pros, simple, useful to measure how much things change. Okay. And I think that's all I'm going to say about it. We have the videos as well if you want to see some more examples. But it's a really useful thing to have in your toolkit anytime you want to see how much something is changing. How much is it dependent on the exact data set I had? You can do a Bootstrap sample and get more of them. Okay. What else? Is there anything else in the data set? Oh, okay. This is one way you can think about the Bootstrap is you can imagine we have the true distribution of the theoretical population, that's in orange, and you have the distribution of the dice roll that you're generating, right? So this is sort of the reason why the Bootstrap works. This dice roll distribution that we created rolling the dice 101 times, should be sort of similar to sampling 101 times. So we would expect that rolling the dice is the same or similar to actual samples from the distribution. And one way you can compare those two numbers is by using the CDF. The CDF stands for the cumulative distribution function. And the cumulative distribution function for the true data is in orange. The cumulative distribution for my dice roll is in blue. And because they are pretty close together, that is why the Bootstrap works. Okay. Any questions or comments? All right, I have one fun little bonus problem here right at the end in the last 5 minutes. So you're rolling the dice over and over and over again. Here is a question about rolling the dice over and over again, which is sort of related to you have a 101-sided dice and you roll it 101 times, something interesting will happen, which is captured in this mathematized question. Bootstrap probabilities. You have 100 data points and we draw a Bootstrap sample with 100 points in it. Which of these is an expression for the fact that data point 1 is chosen at least once? So in other words, if we were doing it as a cards, then we would for sure have data point 1 in there. But because we're doing it as a dice roll, if you roll a 100-sided dice 100 times, you may or may not get a number 1 on there. What is the probability? Which of these numbers is it? I will let you think for 2 minutes, and I will reveal the surprising answer. All right, 30 seconds left to put in your guesses. This is kind of a nice basic probability question about sampling. Okay. What did people say? Big majority on 1 minus 0.99 to the power 100, which is the correct answer. Oh, I didn't put in, oh, I didn't press the right button. There we go. That's because on any individual roll, what is the chance of not rolling a 1 in one roll is 99%. So for you to not roll a 1 100 times in a row would be 0.99 to the power 100. That's the chance of not ever hitting a 1. So what is the chance of yes hitting the 1 at some point? It's 1 minus that. The reason this is exciting is 0.99 to the power 100 is a nice number. Let's do it in Wolfram Alpha. 0.99 to the power 100. What is that? 0.36. Seems kind of like a boring number, but actually this is a very exciting number. Does Wolfram Alpha know what it is? No, it doesn't. That's exciting. We're smarter than Wolfram Alpha here. I'll give you a hint. Let's do the reciprocal of this number. 1 over 0.99 to the power 100 is 2.73. This is a very exciting number. Does anyone know what number this is getting close to? 2.73. Someone said it. It's E. This is E. What's the value of E? Let's do E. 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 2.718. So in fact, if you, let's do a little Desmos to plot it. If you plot 1 minus x to the power x, we were doing exactly that when x equals 100. 1 minus 1 over x, rather. This will get closer and closer to the number 1 over e. So if you y equals 1 over e. So what you're doing is when you roll many, many dice, the chance of every individual point being included or not is related to 1 over e, 36.7%. This is a very famous percentage that appears in probability, and it appears in the Poisson distribution and many other things, but it also appears in the Bootstrap. So the chance of any individual point being in your sample is 1 minus 1 over e. That's the conclusion. This number is so close to 1 minus 1 over e that it might as well be 1 minus 1 over e. Okay, there's many things you can do with the Bootstrap. It's a fun little topic, fun little side quest. On Wednesday's class, we're going to go back to the main story. We're going to do probability classification trees as a fun little thing. And then next week, we're going to start regularization methods like lasso and ridge. Okay, that's where we are, and we'll stop. I'll see everybody on Wednesday.